As promised in the last video, what we're going to do is draw our little tiny box blown up so that we can see it and calculate the flux of our vector field out of the box. Now what we're going to do is one part of it very, very carefully, and the other sides will be very, very similar. So here we go. I'm going to draw a box. Box looks like this. This, and it's got like this, and like this. Now, if I want to calculate flux out of this box and there's no shortcut, I actually have to calculate the flux out of 6 sides: the top, the bottom, the left, the right, the back, the front. What I'm going to do is try to do a very, very careful job doing the top and the bottom, so you can see what's going to happen and the way we're going to do it. And the left and right and back and front will be very, very similar. So what I'm going to do is back in this corner way back there, I'm going to label the point X, Y, Z. Now the reason I need that point X, Y, Z is so that I can actually calculate the arrow. The point on top just above it has different coordinates, but not much. It's going to look like X, Y, Z plus delta Z. Here we go. I can write Z plus delta Z. And again, what I want is to draw the arrows there. So what I'm going to do is say, let's say we're going to draw an arrow from the vector field. And remember, that doesn't have to be perpendicular. It can be very strange looking, right? And the one on top is going to be a little bit different. This is a small box after all. And I just want to say which these vectors are. Now the vector down here, right here, is the vector we get by plugging x, y, z in. So this vector is going to be f1 x, y, z I plus f2 x, y, z j plus f3 x, y, z k. The vector up here is slightly different. We get that by plugging in the top point up there. That's going to be the vector f1 x, y, z plus delta z I plus f2 x, y, z plus delta z j plus f3 x, y, z plus delta z k. Like that. Now remember, what we're trying to do is calculate flux. So the way we do calculate flux is we always take the velocity vector and then we have to dot it with an area vector. Now the area vector on the bottom isn't that hard to come by, because since it's perfectly horizontal on the bottom, we see, for example, a vector that's pointing in the right direction would be minus k. Now an area vector can't just point in the right direction. Its length has to be equal to the area of the region it sticks out of. Well, it sticks out of the region whose length is delta x and whose width is delta y. So this is going to be delta x, delta y minus k. And to find the flux on the bottom then, say we'll call it the flux out the bottom. Remember, this is just an estimate, but it's a good one. It should be this whole vector. So f1 xyzi plus f2 xyzj plus f3 xyzk dotted with this vector. Well, I dot k is 0, j dot k is 0, so the only thing we really have to worry about is the third part. And what I'm going to get is minus f3 x, y, z, delta x, delta y, like that. So that's the flux out the bottom, and we got that by dotting it with the bottom arrow with the bottom area vector. The area vector on top is very similar in style, right? What we need is a vector that's actually pointing due up, right, and whose length is equal to the area of the region it sticks out, right? So the area vector on top should be something like delta x, delta y times plain old k, and then the flux out the top is going to be this big red vector up here. So that's f1 x, y, z plus delta z I plus f2 x, y, z plus delta z j plus f3 x, y, z plus delta z k. Remember, that's just the arrow we get when we plug in the point x, y, z plus delta z, and we get this arrow. So that's all of this red stuff is just this arrow. I want to dot it with delta x, delta y, k. Let's put a little brown thing around here so we know we're going to dot it. When I take this big vector over here and dot it with this vector over here, I dot k is 0, plus j dot k is 0, plus all I'm left with, again, is something involving f3. So what I'm going to get here is f3 x, y, z plus delta z. Remember, we're dotting, so I'm just going to get delta x, delta y. So I'm actually done using the box and the picture to estimate the flux out the top and the flux out the bottom. So I'm going to get rid of that part of the picture, and we're going to make sense of what we get when we add the flux out the top to the flux out the bottom. And we're going to call that the flux out the top and the bottom. And I'm just going to add the two. Well, they both have a delta x, delta y. When I pull that out, what's left is f3 x, y, z plus delta z minus f3 x, y, z, and I have delta x, delta y. We're going to do the same thing we did with Green's theorem, and the same thing we do with a divergent. Well, we're doing this now. This right here looks like the top half of a difference quotient. You can see that x and y are being held constant, and only z is being allowed to change. So if I divide by delta z, what I'm really doing is getting a really good estimate of the partial derivative of f3, that's just this formula right here, with respect to z. Now I can't just put a delta z down here without putting a delta z up here. So our final estimate for just the flux out the top and the bottom is going to be the partial of f3 with respect to z, and now I have delta x, delta y, delta z like that. Yep, I need a delta z, alright? And now my figures are dirty. Like that. Yay! The other four sides are very similar and aren't really worth going over. I usually have students do this during class, so if you want to, please do it. Out the front and the back is going to be very similar. That's going to be very close to the partial of f2 with respect to y, and that's also going to be delta x, delta y, delta z, and then the flux out the left and the right. That's going to be very closely estimated by the partial of f1 with respect to x times delta x, delta y, delta z. So the flux out of the whole thing, so out of all total 6 sides, should be this plus this plus this, and what we'll do is we'll say the total flux. The total amount of stuff that will come out of that little tiny box just looks like the partial of f1 with respect to x plus the partial of f2 with respect to y plus the partial of f3 with respect to z, delta x, delta y, delta z, and we've calculated all we need to in order to calculate the flux out of the whole surface, because what we have is the total flux out of one box. Now on to summing and telescoping and summing and telescoping and summing and telescoping.